the Atmospheric Metabolic Engine, or AME. This sounds like more than just an update. You called it a bold vision, transforming cities into living filters.
Exactly. It's positioned as a potential paradigm shift.
So our mission today is to really unpack this, see how this AME framework might tackle this massive environmental and health crisis. Okay, let's dive in.
Great. So if you look back, previous big ideas often hit roadblocks. The AME framework tries to directly address 6 key weaknesses where others sort of fell short.
6 weaknesses.
Yeah. First, socioeconomic disparities. AME integrates community-led deployment right from the start. Second, monitoring gaps. It uses hyperlocal PM1 tracking, really detailed. Third, techno-economic validation. It's not just cost. It actually creates value through things like metal recovery markets.
There's a recovery from air pollution.
We'll get into that, yeah. Fourth, governance learning from places like Delhi that target interventions at specific hotspots. Fifth, health scope. It explicitly includes mitigating pathogens, not just pollutants. And sixth, implementation, designing it all to be climate resilient from the get-go.
Okay, that's comprehensive. But you said it's not just filtering. You mentioned metabolic transformation. What does that actually mean?
Right, that's the core idea. Think biological metabolism, but for the air. Instead of just catching pollutants, the AME is designed to actively convert them, turn them into useful byproducts.
So turning waste into a resource. A circular economy for air.
Precisely, that's the ambition.
Sounds incredibly ambitious. What technology actually makes this possible? You mentioned 3 pillars.
Yes, 3 main pillars underpin it. First, quantum-enhanced photocatalysis. Second, engineered biosystems. And third, AI-driven predictive intelligence.
Okay, let's break down that first one. Quantum-enhanced photocatalysis. Now, I know a bit about traditional photocatalysis, like using TiO2. Big limitation there is it mainly uses UV light, right?
Exactly. And UV is only, about 4% of the sun's energy that reaches us. So lots of wasted potential.
So how does AME improve on that?
This is where it gets really interesting. It uses graphene quantum dot, GQD, doped TiO2 nanowires. These materials use quantum effects, basically manipulating light at the nanoscale to become active using visible light. The main part of the spectrum, 400 to 700 nanometers.
Visible light. So instead of just 4%, you're tapping in.
An additional 43% of the solar spectrum. It massively expands the energy source these filters can use.
That's a huge leap. And I read something fascinating. These nanofilters are put into 3D printed mycelium structures, fungus-based.
Yeah, sounds wild, right? But mycelium, the root network of fungi, creates these incredibly versatile, sustainable, porous structures when 3D printed, perfect for embedding the filters.
And the results?
Pretty stunning. They're seeing 96.2% removal of PM0.1, those really tiny, dangerous particles. And they convert almost 90%, 89.7% of Turcock's gases into ammonium nitrate fertilizer.
Fertilizer, wow.
And get this, the surfaces have self-regenerating properties. They can effectively clean themselves using enzymes.
Okay, let's put that in perspective. Compared to standard TiO2, how much better is this?
Significantly better. We're talking 353% higher photon efficiency, so much more cleaning power per unit of light. It hits 37.6% compared to maybe 8.3% for conventional stuff.
And the particle removal.
Over 54% higher removal rate for that critical PM0.1 fraction. Plus, the UV visible activation means it works more consistently, and the lifespan is about 3 times longer, 18 months, versus maybe 6 for traditional filters.
So higher efficiency, works in more light conditions, lasts longer.
Yeah.
That makes it much more practical, I imagine. Lower running costs.
Exactly. It reduces maintenance, replacement costs. It makes large-scale deployment actually feasible, economically sustainable.
And this isn't just theory. You mentioned it's being used in Delhi. In informal settlements.
Yes, that's right. They're deploying retrofittable panels and field trials using systems mounted on bollards near schools powered by small 600W solar arrays showed a 74.3% reduction in local PM levels.
Around schools, that's fantastic. Any specific moments from those trials that stand out?
It's really seeing the difference it makes day to day. You hear from teachers or parents about kids breathing easier. One teacher mentioned being able to see buildings in the distance that were usually hidden by smog. Small things, maybe, but they show a real change in air clarity and quality of life.
That really paints a picture. Okay, let's move to the second pillar. Engineered biosystems. Sounds biological, obviously. How does this tackle pathogens?
Right. This pillar uses microorganisms, nature's tiny transformers, specialized microbial communities. For instance, they use a genetically modified bacterium, GMO Methylobacterium extorquens. It's designed to eat methane, consumes it at 5.7 grams per cubic meter per hour.
And methane, a potent greenhouse gas.
Exactly. And as a byproduct, it produces construction-grade biobitumen. Really cheaply, too, like $0.18 a kilo.
Biobitumen, like asphalt?
Yeah, potentially for paving or roofing. But crucially, this bacterium also achieves 99.8% inactivation of Mycobacterium tuberculosis, the TB bug.
99.8% inactivation. That's incredible. So it's cleaning the air and disinfecting it?
Effectively, yes. And there are other microbes involved, too.
Like what?
There's a synthetic lichen called HY5. It pulls CO2 out of the air 3.2 grams per square meter daily and makes oxalic acid. But it also inactivates 95.7% of influenza virions, flu viruses.
Wow. And you mentioned Nalox earlier.
Yes, algal bacterial consortia handle that. They convert about 89% of Nalox into useful biomass. And they also reduce Legionella bacteria by over 91%. That's the bug behind Legionnaire's disease.
Okay, so you have these different microbial teams tackling different pollutants and pathogens. How are they deployed? You mentioned forests.
Yeah, they're often integrated into things like vertical Miyawaki forests, these dense mini forest plantings. Imagine packing 3 trees worth of biological activity into every square meter.
So you're literally growing clean air and fertilizer and biobitumen and tackling pathogens all in these compact urban green spaces.
That's the concept, synergy, turning city spaces into living filters and biofactories.
It's amazing. Okay, pillar 3. AI-driven hyperlocal exposure management, the intelligence layer. Tell us about the TINE system.
Right. Predictive Exposure Intelligence Network. This is the brain coordinating things. It has a few key parts. First, wearable quantum dot sensors. These give individuals really accurate, real-time personal monitoring of PM1 levels. We're talking 93.7% accuracy.
So I can know exactly what I'm breathing right now.
Pretty much, yeah. Then there's a federated learning architecture. This allows data from many sensors and sources, like from 13 different types of pollution hotspots, to be pooled and analyzed by AI without compromising individual privacy.
Privacy-preserving AI, that's important.
Crucial. And finally, it uses quantum-optimized WRF chem models. These are advanced weather and chemistry simulation tools boosted by quantum computing insights to give highly accurate pollution forecasts.
How accurate?
They're achieving 72-hour predictions with an R-squared of 0.94, which basically means the predictions match reality extremely well, like 94% correlation.
72 hours out. That allows for proactive measures, surely.
Absolutely. And the London case study showed this really well.
What happened there?
Using PINE, they saw a 34% reduction in indoor PM2.5 levels when buildings were occupied. And interestingly, this wasn't just from fancy filters.
No, tell them.
Through AI-driven behavioral nudges. Simple alerts may be suggesting you close a window for a bit because a pollution plume is predicted to pass by.
Smart nudges. And people valued this.
Apparently so. The study found a willingness to pay of about £4.80 for every microgram per cubic meter reduction in PM2.5. People are willing to invest in cleaner air when they have the information in control.
That makes sense. Okay, so we've got the tech pillars. But this isn't just tech, is it? It's tied into economics and policy.
Definitely. The whole AME framework is built around a circular economy model. It's designed to generate revenue, not just be a cost.
How? You mentioned metal recovery earlier.
Yes. Recovering rare earth elements and valuable metals like platinum, lithium, cobalt directly from the captured particulate matter, that's potentially tapping into a market worth maybe $47 billion by 2035.
Recovering lithium from air pollution.
Yeah.
That sounds like science fiction.
It's advanced material science, but it's part of the model. Plus, there's revenue from carbon negative certifications selling carbon credits, an $89 billion market, and innovative financing like pollution impact bonds.
And how does this connect to equity, ensuring benefits reach everyone?
That's built in. Subsidies on the recovered metals, the carbon credits, the fertilizer produced these, can be channeled to directly benefit low-income communities or support uptake by small farmers. The economic modeling shows a positive net present value, meaning it's profitable over its lifespan, even if metal prices fluctuate quite a bit, say by 30%.
So it's designed to be resilient economically. And you also mentioned a multiscalar governance framework, making it work at different levels.
Right. It's not one size fits all. Solutions are tailored. At the community tier, you see examples like the Mukuru settlement in Nairobi. Using relatively cheap AI sensors, they pinpointed local pollution sources and saw a 19% PM reduction in just 6 weeks. Or gender-responsive fuel subsidies cutting indoor pollution by 70% in homes reliant on biomass fuel.
Wow, 70%. That's huge for indoor air.
Then at the municipal tier, you have Delhi's strategy. deploying hundreds of water sprinklers, anti-smog guns in hotspots, even piloting cloud seeding during peak pollution events.
And nationally, internationally.
You see national programs like Sri Lanka's Clean Air 2025 setting specific targets, and at the international level, things like the EU Air Quality Directive exploring blockchain and AI for compliance, aiming to cut disputes significantly. It brings transparency.
Okay, this is all incredibly impressive tech and policy integration. But let's bring it back home. For someone listening, what does this actually mean for their health, their daily life?
The impacts go beyond just easier breathing, although that's key. In Delhi, they saw a 31% drop in rescue inhaler use among asthmatics on high pollution days where AME systems were active. That's a direct health benefit.
Fewer asthma attacks.
Exactly. And mentally, too. Using the AI to nudge people towards green spaces during low pollution windows was linked to a 27% reduction in reported pollution-related anxiety.
Interesting, the mental health link.
And the pathogen control is massive. Remember, the 99.8% TB inactivation, that's a huge public health win, especially in dense urban areas or indoor settings. Overall, the projection for full AME deployment in megacities is avoiding around 89,200 premature deaths annually.
Almost 90,000 lives a year. That's a number worth striving for.
Absolutely.
And you also touched on climate resilience earlier. How does AME help cities cope with climate change impacts?
Well, the integrated climate intelligence can help manage resources better. For example, predicting drought conditions to optimize hydropower, potentially preventing over 50% of losses. And there are synergies. Combining AME installations with floating solar panels on reservoirs, for instance. The panels reduce water evaporation by maybe 77%, conserving water, which the AME's biological systems might need, while also generating clean energy.
Clever integration. And are the systems themselves tough? Can they handle extreme weather? Heat waves, cold snaps, sandstorms?
They seem quite robust. The mycelium structures, for example, maintain over 92% functionality in tests from -25 Celsius up to 48 Celsius. That covers a huge range of climates.
-25, wow.
And the quantum dots are stable too. In trials in the UAE, they showed less than 3% efficiency loss even during sandstorms. So yes, designed for resilience.
Okay, last big question maybe. The carbon footprint. Making all this advanced tech must have an impact, right? So you also mentioned sequestration.
Good point. There is an initial manufacturing footprint estimated around 28.4 tons of CO2 equivalent per hectare treated. That's up front. But the annual operation is actually net carbon negative. The biological components, especially sequester carbon, the estimate is made of 14.2 tons of CO2 equivalent per year.
Negative, so it pulls more carbon out than it emits operationally.
Correct, which means the whole system reaches carbon break-even in just 2.1 years.
2.1 years. How does that compare to, say, traditional industrial air scrubbers?
Oh, it's vastly better. Many conventional scrubbers are energy hogs and might never break even carbon-wise or take decades. The AME becoming a net carbon sink so quickly is, frankly, transformative. It turns air purification into a climate solution.
It completely flips the script, as you said. Amazing. So to wrap up, this atmospheric metabolic engine framework seems to reposition air quality efforts. It's not just a cost, but an investable health asset built on solid tech, economic inclusion, and climate resilience. And it sounds like it's gaining traction with potential discussion at major platforms like the WHO Global Conference on Air Pollution and Health next year.
Indeed. But, as we embrace these really cutting-edge solutions, it does raise important questions for us to think about moving forward. For example, how do we proactively manage any potential risks, like developing really robust safety protocols, nanotoxicology for these new quantum materials? And how do we ensure these systems are truly resilient, not just to heat or sand, but maybe to increasing flood risks in our cities? These are the next challenges to address as we scale up.